Good morning. SPIE, the International Society for Optics and Photonics, was founded in 1955 to advance light-based technologies and is one of the most expressive optics societies worldwide. One of its chapters is based in our institute and run by our students. The lectures happening today are part of the chapter's activities. So, let me introduce you Professor Igor Meglinski. Dr. Meglinski received both his bachelor's and master's degrees in laser physics from Saratov State University, Russia, and his PhD in Biophysics, Biomedical Optics at the interface between this university and the University of Pennsylvania, USA. His Biophotonics group is a member of the OLO Biomedical Consortium, which in turn is associate partner of the Euro Biomedical Infrastructure Network. His research group employs several optical experimental techniques for biomedical purposes, and he kindly accepted the invitation from our chapter to visit our institute and speak to us. Professor Igor, we greatly appreciate your availability to be with us. Thank you.
Thank you. So, and I should say thanks to SPIE. I think that actually support this visit and these activities in your university. So I think it's great. Okay, in the second talk of today, so I will talk about online computational tool for the needs of biophotonics and biomedical optics. That's one of the projects that we work on a long time. And I will explain what our vision and why we actually seriously consider that. But let's think about what actually, what we need really for, let's say, biomedicine. So, and what are the challenges? So we have a number of diagnostic technologies, and that already installed and properly used in the hospitals. And that's, for example, computer tomography or X-ray, ultrasound, MRI, and these technologies are well known, and most of hospitals use them. So what we can say about these technologies? First of all, that's imaging techniques that can give us reasonably good spatial resolution, in terms of like about 1 millimeter. So they non-invasive. So the problem is that they provide us information on a quite late stage of the diseases. Also, here should be possibly another scale saying that they're quite expensive. So we have other techniques like histology, microscopy, that invasive techniques means that we should prepare the slides that slice the biological tissues. They provide us with high resolution, about 1 microns. That it's like in a way of cell size. And these techniques are able to give us information on very early stage. They possibly reasonably cheap, but again, they invasive. And we have endoscopy, and we also, the community is looking for the way to produce the technique that we will be able to give us the information on very, very early stage of the diseases that will be completely non-invasive with very high resolution and again with very low cost. So, and what this technique could be? Possibly some optical techniques and possibly that it will be combination of imaging techniques. And thus, if we think about the optical techniques, so what is the problem? So if we think about the photons and how the photons propagate through biological tissues, so, and if we compare that with well-known X-ray tomography, okay, if we apply a laser and if we want to see, how the light propagates through to make imaging through the tissues, it's a total analogy of X-ray. So the ballistic photons that propagate through, it's very, let's say, low probability. So imagine, when we consider that light propagates through biological tissue or from any tissue, so we have so-called exponential decay that's known as a Beer-Lambert law. means that intensity that incident to the sample and intensity that we detect will be related to each other with this exponential decay. Thus, if we take the human, so we can easily count that we would need to, even for 5 centimeters, so we would need to wait for a number of years to get just one photon, which is obviously not enough for the diagnostic. But we want to actually achieve some images like that. So, and also I want to refer to this picture. So imagine, so this part of the picture from Louvre, from Paris. And this picture is about 400 years old. And you see, so these painters, that time, they clearly understand how the light propagates through biological tissues. At least they was able to, to simply show that. And we don't understand. Or we think that we understand, but we still not. So we know that light is scattering within the tissues if we apply, through one. But again, you see, they have no any lasers, but they just simply, were able to create that, which is amazing. And thus, for a number of years, we did try to understand, okay, so how we can use the light for tissue diagnosis. Means, okay, so we send the photons to the tissue, and then we're able to detect the photons that are coming out from the tissue. And by comparison of the behavior, so we want to know, okay, so what they did inside, and okay, so and what the properties, how these properties, the influence of these photons. And you see, we're able to send photons coherently, let's say, with different color, and we're then able to detect them also with different color, with different coherence. But the question is, okay, so how we can, quantitatively find out what is there. So also, if we think about that, about biological tissues, I also want to show the one picture. This is a picture of Cranfield University campus. And in the UK, United Kingdom, so they are very, in the mornings and evenings, they are very foggy sometimes. And if we look at that, so it's perfect scattering medium, and we always have the part there where we can't see anything. And we have something that we're able to see, and also intermediate part. So, and thus, when we're trying to apply optical technologies for this any testing, so we also consider the 3 different regimes of scattering. So we always have the regime of multiple scattering, when the photons are scattered so many times when propagate through biological tissue or a turbid medium that we're not able to see any patterns. And we have the regime when we have so little number of scattering events when we clearly see the patterns, and we have some intermediates. And okay, so and this again, we in the application of the technique, we have a different implementation of that. So for single scattering, that is typically associated with microscopy. The multiple scattering, when we consider that light have a diffusion through the tissues, like in terms of photons or partial components of the wavefront. And we have some, again, intermediate case that is not microscopy, but it's not, we're not also able to consider that as a diffusion process. Okay, so, and now if we think about how the photons propagate through. So again, for single scattering, we're able to describe the photons as a ballistic propagation, means that they propagate from light source to detector, and they touch on the object of interest once, let's say. Single scattering. So for the multiple scattering, the photons have a random walk and scattered many, many times, and they don't remember what the original direction and if they was polarized or not. So, and we're able to consider that photons in terms of again, diffusion process, which is able to use the particular analytical equations. And those photons that scattered several times, when the multiple scattering is not erased yet, when we're not able to consider them as a diffusion. But it's also not a ballistic photons anymore, so-called snake photons, or like intermediate scattering regime. So that's extremely difficult case because we're not able to apply any analytical solutions for that. And here it just shows when we send the pulse, and if we detect the pulse, so the first photons that are coming with a very short time will be ballistic photons. Then we have these snake photons here, and the rest will be multiple scattered photons. So, and then from theoretical point of view, we're always trying to find the quantitative parameters that could be used to, like parameters that are able to characterize the tissue. What is that? So again, the key law is a Beer-Lambert law, or Beer-Lambert-Booger law, so which is, again, exponential decay of intensity that coming in and coming out on the detector. And here we have the attenuation coefficient and thickness of the medium, let's say here. And traditionally, so now we consider that attenuation has happened due to scattering and absorption. And it could be presented here just in terms of cross-section of scattering, a number of particles, and cross-section of absorption, again, a number of particles. So for some reason, we use so-called optical depths when we consider, okay, so how this attenuation coefficient is relates to the path length within the medium. And again, we defined these three cases for a number of these optical depths or number of scattering events, average scattering events in each. So why we do that? So basically, this coming from the way of development of the theoretical part of description of how the light propagates through the medium. And one of the, let's say, the well-known way is based on the radiative transport equation. What does it mean? So it's a very simple and it's a phenomenological model. So if we have the medium, we illuminate it with light, and we're able to detect the light on the detector. And then we consider, okay, what happened? Okay, so the sunlight that come into the medium will scatter and will never come to the detector. So it will be lost somewhere in the medium. And thus, we describe this term with a minus. So this light is not coming to us. So some light will be absorbed, some photons will be absorbed, and also will never come to the detector. And okay, so another minus, so absorption, and this is scattering. And there will be some light that, due to multiple scattering, will have a number of traveling through the medium and will come to the detector, but with a different directions. So thus, we're able to describe these terms with, again, scattering, and then this phase function means how the light is changed the direction due to the scattering. And thus, its equation very simply describes the energy component, means we sent this intensity, we've got that intensity, what happened with other intensity within the medium. And originally, this equation was involved to develop, again, optical tomography system that is total analogy of computer tomography for breast cancer imaging. So X-ray or CT tomography is well known, and it's produced by a number of companies, like, for example, General Electric's healthcare, or let's say like the Philips and many others, with the obvious target to detect low contrast tumor. And we actually, again, with Professor Britton Chance from University of Pennsylvania, who was one of pioneers of the idea to develop this optical tomography, started to develop this, again, optical tomograph. So that's our first samples. So when we have a number of, detectors and light source, so we send the light and we detect the light around. And inside, we have some inclusions with different scattering absorption properties. And we did try to solve this problem in inverse to this just simulates the, let's say, presence of cancel, let's say. And with this radiative transfer equation, we, in principle, we're able to solve this problem. So, but if, again, we think about it, so there's a number of other ways. So we can use this electromagnetic theory, the transport theory, and this, like, more analytical ones. So here we should use the Maxwell equations and possibly apply this Mie scattering. In the transport theory, we can come with this Boltzmann equation. So this is just a simplification of the solution and use the diffusion approximation. And we also have the stochastic methods that's, again, based on, let's say, Monte Carlo or random walk theory. So, and there are a number of theoretical approaches. What is the problem? If we think about the biological tissues, so let's say skin, we have a very complex structure. So you see in the skin we have the different layers with very irregular boundaries and distribution of collagen, for example. And here the packing of collagen could be different through the depths. And thus, to solve the equations, we need to find out what are the boundary conditions. And for most of biological tissues, it's physically impossible to create these boundary conditions. All these boundary conditions will be far from the reality. And thus, at the moment for the description of how the light propagates through biological tissues, the most versatile solution for simulation of this optical radiation propagation in complex medium, like tissues, is a Monte Carlo technique. Okay, so, and many applications or many developments associated with development of new optical technologies for diagnostic purpose are focused on the Monte Carlo technique for validation, for understanding, for many issues. And from my personal experience, what we have, if the student is coming to do PhD studies, and he or she considering the particular optical technique for particular application, on some stage of the studies, they need to do computational study like Monte Carlo. Great. And, okay, so he or she did some preliminary experimental studies and then switched to modeling. And everyone doing modeling and modeling and modeling and modeling, and by the end of the 3 years, 4 years, we have some experiments and some Monte Carlo modeling. That's it. And we said, okay, so we did also these studies, a number of years. We also developed Monte Carlo models. And now we decided, okay, to make it online available to everyone. And thus, if the typical application, the students are able to come and use these solutions for the purpose. And they will save the time simply for the development of experiment or development of some case studies. And thus, this might talk about online solution for the needs of biomedical optics means that we develop this Monte Carlo-based technique for modeling of light propagation in tissue-like biological medium. And I will just explain with here so how it works and what we do. Again, so about Monte Carlo itself. So actually, if you ask someone, who was the first who used Monte Carlo, there's no particular answer. So we believe that it was originally started from Enrico Fermi group when they consider some neutrons propagations. So, and that was also suggested in terms of energy. So, but maybe in the most known, also the works they printed and available for reading are associated with the names of Stanislav Ulam, John von Neumann, and Nick Metropolis when they worked on so-called the Manhattan Project, means they considered this hydrogen bomb and how these nuclear reactions happened. So and then this solution that was suggested by this team was implemented on other relevant techniques for atmospheric optics and geophysics, considering how the energy propagates through this medium. And about from these years, with the name Robert Nozzle, Robert Bonner, Britton Chance, Brian Wilson, Sichao Feng, Marlene Kaiser, Scott Prowl, Steve Jacques, Li-Hong Wang, and Valery Tuchin and others. So this Monte Carlo started to be used in biology and medicine, mainly to understand how the temperature is distributed within the skin tissues or biological tissues for photodynamic therapy dose counting. So that was the first applications. Now it's 1,000 papers per year in a different application. So that's just the pictures of this pioneer from Enrico Fermi, Stanislav Ulom, Metropolis, and others. Okay, so, and just briefly about the key stages. Again, this Monte Carlo is a total analogy of radiative transfer equation, the standard technique. So first, we use this optical radiation and is defined like a photon packets. Why photon packets? So in terms of physics, we're not able to, we have two stages for photons. Photons can be absorbed or can be scattered. Thus, if we consider how the photons propagate through multiple scattering medium, we're not allowed to use the definition of photons. Thus, we use the photon packet, means when they propagate like a group of photons. Some will scatter, some will continue the propagation. Okay, so, and again, photons propagate through scattering medium with initial parameters that are corresponding to the light source. Means it could be geometry like radius, distribution like Gaussian, polarization, and anything else. And then what we do, we count the trajectory of photon that is again governed by probability density function. So that associated with absorption properties, scattering properties, and the phase function that could be used different. For small particles, we're able to use Rayleigh scattering function. For bigger particles, Mie scattering function, or Lorentz Mie scattering function. But very often we use the so-called Hine-Greenstein phase function, which is just the averaging process for simplicity. Okay, so when we're talking about detection, so we want to know some basic things like, for example, how many scattering events happened within the tissue for particular trajectory. So, okay, so we always need to know the final photon position and its direction, how it came to the detector, and total path length. And then, again, so we're able to solve this equation with this Monte Carlo technique. Okay, if you open Wikipedia, so they will be suggested this standard diagram, how it works, which is again, so we launch photon, we determine the step size, like, okay, so we launch photon in the point of the incidence, so then we determine how it goes through, then we change some weight, means that each photon packet described as a weight function, and original weight will be becomes smaller and smaller and smaller on each part, and then when it's coming to the detector, it could be very small. So here they use the so-called roulette system, means if the weight function is very small, they considered, okay, so to give a photon additional chances to go to the detector or not. So this is a classic scheme that just repeats the, radiative transfer equation. And what we can do with that? Imagine, so if we have the medium, and we simply divide this medium by elementary volumes, and each volume can be filled with the actual number of scattering particles of particular size, particular distribution, density. And then we send these photons from one by one, and we're able to see how it's propagate, each photon pocket through these elementary volumes and how they interact to each other. And then we're able to detect the intensity and with any particular size, and thus we're able to see or estimate, how the photons goes through the medium. Again, here, just the same as I mentioned before. So we send the photons that come into the scattering particle. Then we use the particular phase function to select what angle is scattered, and to find out, okay, how long is this propagation to the next scattering event. We use so-called this association with the scattering events and to count the free path lengths with this random number. And that random number is why the Monte Carlo is called Monte Carlo, because we use this random generation. And that's actually a very powerful technique, so because we're able to use it from single scattering to multiple scattering. Imagine here, for example, if we illuminate the elementary volume with one particle, we're able to count how the photon packets are scattered and what they will form in terms of, let's say, scattering function on any part of this elementary volume. And actually, this phase function is one of the important parameters. Imagine, so here is this our medium when we send the light, and here what we scattered. And if we'll consider this front phase, so I mean here, this is a back one where we sent the medium. This is like a cross section, and this one is just shows the same picture. And here, the phase function, how the indicatrice of scattering is changed on each scattering event. And if we start with small particles, and a second. Okay, you see, so here the phase function is changed, and we're able to see how the wait a second. Okay. How the collective behavior of photons through the medium is changed with the forward scattering. And the question is, okay, so how correctly I'm able to feel this medium and what I can do? And you see, we're able to prescribe homogeneous or inhomogeneous medium with monodispersed particle, polydispersed, or let's say uniformly polydispersed, or the combination. And for that, we need just, the clearly change the model. So, and thus we started, let's say, from the simple one, like for homogeneous medium. Then we develop other and other when we're able to consider the different distribution of particles within the medium. What does it mean? So imagine, so we're able to do the distribution of size of the particles around the particular diameter, let's say all the particles like 40 microns. Or we're able to produce more smart distribution of particles for some reason, or even more different that are distributed through the medium. So, but that was like the, let's say, original test of the medium. And then if we come to the real tissues like human skin, we will never find the particles at all. So the collagen fibers, there's some melanin, some membranes, the boundaries, the roughness of the skin, but not the particles. So what we also have here, because of different layers, and these layers have different optical properties. And thus we should consider basically not this model in a more different way. So we should implement here the layered structure. And actually this shows the known and well-confirmed the layers of skin from stratum corneum to reticulodermis and subcutaneous fat, and then there's some muscles and bones. So, and originally we introduced a very simple model based on the waveness or roughness of each layer, and we're able with this very simple mathematical way to create the surfaces that shows the difference between the layers, and obviously that then we're able to consider here reflectance or refractance of light on that. So the other important parameter is blood. So if we look through the skin, the blood vessels are not distributed uniformly. So we have capillary loops here, for example, that are closer to the surface, and we have veins and arteries that distributed through the reticular dermis. So you see that if you look on the capillary loops, that's capillary loops of monkey, really, so, but very close to human ones. So, and they have quasi-periodic structure. And thus, on some layers, we're able to count precisely the volume of blood and how it's actually affect the optical properties. And we implemented this distribution also in our model. So, we're able to, basically from biological studies, we're able to count, so the changes, gradient of the blood concentration through the thickness. And then, again, if we know that, so we're able to estimate, so how, what the absorption and scattering properties on each layer. And again, so linked it with a particular, the vessel's distribution. And thus, our, let's say, model that we originally developed, so was focused on the distribution of blood and the difference between the boundaries of the vessels. Then we know that the main chromophores in the skin is oxy and deoxyhemoglobin, water, melanin. There's a two-form, eomelanin and pheomelanin, and the other chromophores that we can say like a baseline, and they have a different absorption properties. And thus, we see if we consider our model, we're able to again introduce this thickness of each layer that will be associated with the average thickness of real human skin. So we're able to then measure refractive index and put it like for each layer, concentration of blood, saturation of blood, hematocrit parameters. So this like, so there's two parameters that are associated with the presence of hemoglobin within the one particular red blood cell and concentration of water through each layer. And based on that, we're able to estimate what will be the absorption of each layer within the skin for different wavelengths. Okay, fine. And the same we can do with the scattering properties. Absolutely in the same way, based on the, let's say, the actual diameter of collagen fibers or presence of melanin or granules. So we're able to estimate how the absorption and scattering can be there. Okay, this is for scattering. Also for different layers. So again, as I mentioned, we very often use the Henne-Greenstein phase function, where we use the one of the parameters called anisotropy of scattering, and it also will change from the layer to layer, but they're very, very similar ones. And then, implementing this to the Monte Carlo, we're able to count the, let's say, reflectance spectra, and from this spectra, we're able to correspondingly find, so the color of skin and how it's changed. For example, here, with the presence of melanin. So when we change the melanin concentration in one particular epidermis, so we're able to see how it's changed. If I want to change the concentration of blood, or if I want to change the blood saturation, we're also able to see in terms of spectrum, in terms of color changes of how the skin reacts. And of course, from this data, we're able to do a number of, let's say, studies. So, and we're able to consider that how the skin changes within a particular color scheme, RGB or LAB. And actually, from our study, we found that you see, so if we do the measurements of, let's say, color of skin in the, let's say, near infrared parts, so we're able to see that with the eyes, but it's not count to or the triangle. So these points will be out of there. Whereas on the LAB, they will be exactly, seen by the scheme. So means what I want just to say. So if you work with this color coding of spectra, so be careful because it's some this coloring they show some artificial colors rather than the actual ones. Okay, so how Monte Carlo is good enough? So you see, so when we consider with propagation of light, as we discussed through this cube, and on the front page, so for the experiment, we're able to see that changes of laser beam through the scattering, and we're able to, I would say, imitate the propagation of particular laser beam through the scattering medium. So for different, again, density, optical density, how many scattering events have happened. So that's in terms of validation. So we're trying to develop the tool that will be not just simulate the light propagation, but we want to imitate how the beam profile or how the actual experiment could be developed with the modeling. And also, when we talk about the skin reflectance measurements, so we're able to select the optical properties for skin in a way that we're able to measure or again mimic the reflectance spectrum for the particular device. For example, here the Ocean Optics standard spectrophotometer with that probe, and we're able to observe we're able to imitate the reflectance spectrum for that probe. And also, our particular interest was, okay, so, and what we really measure under the skin. And with Monte Carlo, we're also able to observe the localization of detector signal within the medium, means what actually, where the light is coming from to the detector, and we called it sampling volume. Okay, so, and here is just another view. Imagine, so if we change the distance between light source and detector, for example, here the light source and detector have the same fiber. So light is coming here and coming out. Here they stay very close to each other, one and another one. And then we separating them, separating, and we're able to see how the area of detecting area is changed. And here we're able to link it with the changes of the reflectance spectrum on the detector. So why do we need it, really? Imagine I want to create the sensor, okay? And I want, with my sensor, to observe only the changes of blood flow or some parameters like oxygenation, deoxygenation, within the capillary loops only. And I don't want to see any further. So why capillary loops? So because many physicians believe that the changes of blood parameters within capillary loops can be used for early diagnostics of many cardio diseases. Okay, so this is our target. And the question is how I should design my fiber optics probe here to detect this area within the skin. Okay, imagine, so if I put the one fiber and close another fiber, so my light will goes somewhere here, and I will measure this option. Okay, but if I just simply slightly move these fiber optics, so you see, so this my effective area of detection will be slightly different and will touch mostly the capillary loops. And what will be the difference, and what will be the optimal design of the fiber optics probe? And with Monte Carlo, we're able to simulate the distribution of this, again, sampling volume for the particular geometry of fiber optics, for example, or for confocal probe, and see, okay, so where we're able to localize the detecting volume within the tissues. And then we're able to find out, okay, so if we do it with particular angles and how this detecting area will be changed. And this will give us a tool to estimate the efficiency of that development of the probe. So, for example, here we're able to predict, okay, so if we have the focus light here and this, the area, and what happened if we change the scattering and how this, focus light will be localized with the medium. Okay, fine. So the other aspect that was considered for a number of years is the application of Monte Carlo for so-called inverse problem to observe the tumors and their localization. And actually, again, we worked for a number of years, and I should say that it was finally developed, and we were able to create even the prototype, and Philips company considered this prototype for the application for, again, breast imaging to observe the tumors. And what happened when we started to talk to physicians, they said they don't need that technique. So the reason is that because this, again, Monte Carlo, and this code was based on the diffusion approximation. Diffusion approximation have a limitation. So it will be able to see the object within the scattering medium if the actual size of objects is about 10% of total volume. Means, for example, if we have 1 centimeter tumor, we will perfectly see that if this, let's say, diameter, let's say, 10 centimeters. But if it will be less than 1 centimeter, it will be not seen properly. And 1 centimeter tumor is a perfect developed tumor, and practitioners, clinical practitioners, they don't need any technique to feel if they're tumor or not. Even patient herself able to say, okay, so there's something wrong. And okay, so they're saying, okay, so why should we buy the system that's not able to see the early development of tumor? Also, tumor is not always like a sphere. It could be very complex, complicated, the shape. Okay, so that was not good for us, but we then switched this technique to the brain studies, and with the brain, they're more, interesting way. So we use it to understand how the light propagates through the particular way. So, and you see, so it could be done mathematically. Again, so the idea is to observe the different zones within the brain. And what is the problem, actually? If we do that modeling, so for the particular fiber optics, and we want to understand, okay, so what changed here and what we will see on the detector, we send one by one all these, all these photons. And again, we're able to, with the current developments, we're able to observe the changes on the detector for most of available techniques. So, and thus, by knowing the distribution within the medium, so we're able to predict, okay, so what tissues make an influence on our detected signal, and we're able thus implement it for diagnostic problem. But what is the problem here? It's very slow. So to use this simulation and waiting when we will get the solution, so we should implement a lot of computational time. So, and then we started to think, okay, how to optimize it. So the one of the obvious way, so which is quite simple. So when we consider this trajectory, we're able artificially consider then what would be the signal that come in from each scattering event, which is not related to the Monte Carlo modeling. It's like a part of we call semi-analytic approach. So that's works very well. So because we then need to very very quickly count these signals, so we need less amount of photons propagation here. But the problem is if we have multi-layered medium, we should always consider the reflection and refraction on the boundaries, and thus it will be more complicated to implement. So it's roughly impossible. And then we started to think, okay, so what other way to speed up our modeling? And then if we think about how the standard computer is working. Imagine so we have the one CPU, the core, central processing unit. So, and we basically on our computer, for example, you have Microsoft Word. When you do some paper writing, you run Monte Carlo. You use MATLAB for some reason. So you have possibly some other processes like Internet Explorer, some other thing like, and you always have some reservation of time for system work. And in that case, so the detection of single photon packets will be in that range, about 100 milliseconds. If we have a more advanced computer with, let's say, 6 CPUs, so it will be quicker, and we can reduce it, proportionally to the number of CPUs. If I'm smart enough and I have a real computer skills, I can assign these CPUs to be focused dedicatedly only on Monte Carlo. And in that case, I'm not able to use it for any other purpose, for Internet, for Microsoft. So it will be only focused on the calculations of Monte Carlo and some the system needs. And in that case, we're able to, again, to reduce the detection time and come into the range of 1 millisecond, 100 times less. Okay, but now there is a new opportunity to use graphical processor units, so-called GPU. And what does it mean? Actually, what I was always surprised, so when my kids are playing in the computer games, and when someone's shooting, and the bullets are going, and then they reflect from some wall, and we see the trajectory even. And if I want to do similar Monte Carlo to see the trajectories of photons on a screen, it will be very, very slow, much slower than on the games. And we started to investigate how they did it. Okay. And we found that, okay, so first of all, they use this GPU unit when they can artificially select the number of artificial cores that will be each dedicatedly work on the particular count. And for example, if I do this Monte Carlo, so I can do it like 124, and each one will be, produce the one calculation only for Monte Carlo. And of course, in that case, when we implemented this, so we're able to come to counting to the way of microseconds. And additionally, we're able then to implement parallel programming on this GPU when each core simulates the separate, let's say, photon packet. And thus, if we compare with traditional, when we send one by another one, in parallel computing, so we're able to simulate the many of them. Even more, for example, here we're able to put the particular distribution of initial light intensity, for example, Gaussian, with a particular coordinates or image that will go through the scattering system and comes to the detector very quickly. And then, based on that, we come into the concept of this online Monte Carlo computational tool for the needs of biophotonics and biomedical optics. So what does it mean? So we previously, We previously developed a number of applications for sampling volume studies, for skin spectrum, skin color, some OCT, pulse oximetry, and many others. And now we said, okay, so why students need to do that again and again? Okay, so they should come to that tool, click on the particular application, and if they need to, they can use it for the purpose. Okay, so how it works now? So, okay, so you selecting this one of the application on the web browser, so and it goes to the server, and then it relates to this GPU unit that actually do all these calculations. For example, in our case, it looks like that. So you press in here, then you come into this application. For example, here the skin spectrum. Then we suggesting the simple tool. So if you want to start simulation using our parameters, optical parameters for the skin tissue, so you can do that. If you want to change and you want to select your own that associated with a particular diseases, you can do that, or you can return and choose another application. So then if you want to choose, so you come into the optical properties that we assigned for each, let's say, layer for skin, and you can change the scattering, absorption, the anisotropy parameter, and refractive index, thickness. You can add the layers, you can make more number of layers, and many others. So then, when you select that, so we have also special table for blood distribution within the tissue, so, but also it could be changeable, and melanin, let's say, the concentration. So, and then when all the parameters are set in, so we suggesting also to select so what you want to count it for which particular probe. For example, if it's fiber optics probe, or detect diameter of light source probe, so the diameter of detector, what is the separation, what is the numerical aperture here. So it's also can be employed. And then it's just how you would like to plot the graph. So should it be just one part here, or all this sampling volume? So, and then when you're ready, so you start the button, and it sends to the GPU unit, which is now in the cloud, and you're able to get these results, for example, for the skin counting. So polarized light. So currently there is a number of techniques that using the polarized light, and what we talk about, so in radiative transfer equation, there's no polarization at all. So, and we also started to implement this polarized light to Monte Carlo. And I'm just to remind you, so when we think about polarized light, so we send the polarization, and we analyze light using the, let's say, also polarizers that we called analyzer in that case. And when we think about polarized light, we have basically different stages. We have like line polarization that could be vertical, horizontal, and if we consider circular polarized light, we should consider the phase difference between X and Y, and it will be left or right-handed polarized light. Okay, so and how we can implement that to the Monte Carlo? So, and here we should consider the so-called the waves properties, that's waves properties in 2-bit medium. Okay, so again, typically when we think about wave propagation, it's, for example, like that. But if we consider the medium with absorption, so the amplitude is changed. However, the wave properties will be, again, they're preserved. The similar could be applied for the circular polarized light. But in reality, if we think about the medium, let's say there could be a very different way. Imagine, so when we have birefringent medium, so this X and Y components propagates differently, and thus we will have the very complex, the signature of wave that propagates through the medium. Also, if imagine, so here, let's say the interference between linear wave and circular wave also produced even more complicated ones. And the question is, are we able to separate that cases and implement in the modeling? So the answer is yes, but it's not like so easy, okay? And also I want to remind all of you the also fundamental property of light that we very often ignore for some simplicity. If we think about how the light, polarized light, interact with the medium, let's say this is this is a medium that have different refractive index. For example, this air, that refractive index is 1, and here, let's say 1.5, like a glass. And what happens? So the orientation of electrical field component will produce us different reflection. So if it's coming, let's say, for these transverse and transverse magnetic components, TM and TE. So, and this is well known, and this is standard Fresnel equations. Okay? So, but these equations gives us only the amplitude for reflectance. What we typically ignoring that when this polarized light interacts with the medium, we have also consider phase shift between X and Y components. And here, for example, they shows that, okay, so for the case when the light is coming from the medium with low refractive index to medium with high refractive index, so we have that situation that for TE we have no phase shift, but for TM we will have phase shift since the particular angle. And if it goes vice versa, so they will be more complicated. What does it mean really? Imagine if we send the wave with the two, let's say, component, let's say X and Y. Okay, that will be the polarized light. When it's coming to the medium, these two components will have the phase shift, and thus, if we consider reflected light, so the one of component will preserve the direction, and one will be completely changed for 180 degrees. If we consider propagation, they will be more or less preserved. So, and then if we consider the circular polarized light, and we have the shift between these two components, let's say if we send the right circular polarized light with the shift here in the phase, when it reflects, it will change the helicity. If it propagates through, that will preserve helicity. And we should implement it. So what does it mean? Again, if we consider our case here, so that's what happened. And we think about the scattering. There also happened the helicity flip. For example, if we consider the release scattering, and when the light is scattered forward, it will preserve helicity, and if it's scattered back, it will change the helicity. And thus, in a scattering medium, when we have a number of scattering events, and we, let's say, send the right circular polarized light, if it reflects, okay, it changes helicity. If it's scattered, if it propagates through the medium, it will preserve. Scattered forward, preserve helicity. Scattered back, change helicity, and scattered forward, okay, preserve helicity. Thus, we will have some components that will change helicity. However, there could be the case when it's scattered always forward, and it will preserve helicity. And the case when we have twice, let's say, back scattering is also will change. And thus, that means that even an odd number of helicity flips is important here. And we should implement it in a model as well. On the other hand, so, we always have, like on the detector in that case, if we send the right circular polarized light on the detector, we will see a combination of or product of the co-polarized means the, let's say, right circular, and those that change the helicity. If they portions of that part of the light will be same, on the detector we will see the linear polarization. If one will prevail, so we will actually see the elliptical polarized light. Okay? So, and actually in our case, there's a central central issue. So when we consider the light scattering in tissues for normal and abnormal, the thing is that for normal tissues, so the size of nucleus that are main scattering the line particles, they're very close to release scattering. If the cancer has happened, so the DNA within the nucleus are changed. And what happened? So the dielectric constant is changed, and refractive index is changed. And thus, the scattering will be changed as well. But very often with cancer, the nucleus size becomes bigger. And thus, even with all these issues, so the scattering for the cancers becomes mis-scattering, means scattered forward. And thus, again, if you remember, so I'm just showed this the picture again. So when we consider the let's say for particles with the cancer, so you see the peak of scattering forward will be more let's say important parameter here. And okay, so and in reality, if we consider increasing of the particles, so we will have not only one helicity flip. So even if the light is scattered in a side, so we will have number of these helicity flips, but it also can be counted and implemented in a model. And thus, we use here the so-called Stokes vector formalism when we consider, okay, so how the polarization is changed during the propagation through the medium. And just to remind you what is the Stokes parameter, so the Stokes parameter coming from the way of measurement polarization. So when we consider X and Y components, as we just for polarized light, so they sum we call it like total intensity. The difference will give us the second component of the Stokes parameter. Then if we consider the product in a rotating with 45 degrees, will be third one. And this parameter, the last one, shows us the difference between let's say, right circle and left circle. We call this parameter, it shows the helicity flip. So on why it's used? It's used traditionally because with this Stokes vector, we're able to describe all possible states of polarization of light. And Poincare sphere used as a graphical tool of presentation. Okay, so what we have. If it's pole, let's say it's right circle polarized light. If it's south pole, left circle polarized light. On equator, it will be linear polarization. And in between, we have this elliptical light. And now there are a number of studies when they used like the incident light and light with detector, which is linked to each other with so-called Mueller matrix. And what is Mueller matrix? Another way, so here, light source, light detector, and that Mueller matrix means our medium and how it's changed the state of polarization. And Monte Carlo, we're able to simply reproduce that changes. Okay, so, and why we need this Monte Carlo? So basically, when we consider the results of measurements, so we should clearly understand, what actually we measure, especially when we're talking about the medical problems, to avoid this scenario of interpretation of data. Okay, so and we did a number of these theoretical studies to understand the formation of, let's say, multiple scattering signal in terms of this helicity flip and this in terms of polarization, a number of scattering events, and we found, you see, so that so with the increasing of scattering orders, we able to see how many flips and how that will relates to the formation of signals. So, but what I want to say here, you see, even that it's so complicated, we're able to, with Monte Carlo, implement it clearly and estimate how it happened. And again, so this again just show that in our case it's also important not only the polarization state, but we also should find out the interference phenomena because if we can see the coherent properties of light, as we mentioned on the previous, so the interference will be important, and this interference term that will produce us the speckles is again important. But here again the same issue that I'm already mentioned on the previous one. So, but the phase of this phase difference depending on the path length and orientation of vectors is hugely important for the polarized light. Again, just to remind that we have constructive destructive interference, this phase changes, and which shows us fluctuations. Okay, so and now if we think about this interference and coherence properties of light that we're able to implement, and here maybe on a previous lecture it wasn't clear, but here you see we're able, if we change just these parameters, coherent properties of light, so we will able to see very clearly the patterns for core and cross-polarized light and this depolarization ratio, or we're able to observe speckle formation. And of course, when we think about how the light propagates from the point of incident to point of detection, so this parameter is important. So as we know, if this distance, path length difference, is bigger, the coherent properties of light, so we will have more stable the detecting signal rather than when it's small one that produce the fluctuations, again known as the speckles. Okay, so and again here is also possible to compare Monte Carlo versus analytical solution, and that will also have a very good agreement. The only difference is here that in Monte Carlo now we're able to implement the speckles formation. In analytical solutions, they consider the, let's say, so-called scalar, the light, means no phase properties of the light can be considered. Okay, then roughness of the surface of skin or other medium is very important. And we're able to, again, to introduce this roughness in a particular way when we are able to create the roughnesses that are very similar to the actual biological tissues. And thus, we're able to see how the polarized light is distributed for core, cross-polarized light, and what actually the path length difference, which is like analogy of depolarization ratio within the skin, means if we operate core polarized light or cross-polarized light, how deep are we able to see within the tissues with a different roughness, for example. And even more so, we're able to observe these helicity flips, the fundamental parameters that how the light propagates and comes with the different changes for different size of the particles, and it's just another presentation of polarization in terms of Poincare sphere. So how this changed the signature of polarized light when we able to when we changed the particle size within the tissues. So okay, so why we need it really? So I understand this is boring possibly for you if you're not involved in this polarized optics. So, but imagine, so with all that theoretical studies, we found the way that we able to estimate how the light propagates through the scattering medium and how this polarization changed and what we will be able to see on the detector for cancer and non-cancer tissues. And that gives us a way to create this experiment with optimal parameters. So means we're able to predict roughly, so okay, so what lens do we need to use to focus light, where we should detect the light to make sure that there will be absolutely stable signal in terms of polarization and the fluctuations of the intensity. And now we come into the other let's say, way to simulate not only the just simple polarized light, but we also now consider the so-called Lager-Gaussian beams. So what is the difference? So if you remember, we consider, when we're talking about the polarized light, we consider only one stage of polarization. In the Lager-Gaussian beams, it's a special beams that we're able to do the distribution of polarization state across the laser beam. It could be, for example, like here, or it could be changed many times, and means that it's like a twisted light or spiral that propagates through. It's much complicated than just the circular polarized light. And what we think, so when this light propagates through tissues, so we will be able then to see not just one stage of polarization, but many of them. And for example, here, you see, we send the light, and if there's some particular orientation of, let's say, birefringency, so some stages will be filling of that birefringence, some not. And on the Poincare sphere, high-order Poincare sphere, we will be able to see how this original polarization state is changed, and thus we're able to see the, let's say, the more easily the property of tissue. Okay, so in the summary, what I want to say. Again, Monte Carlo, we're able to simulate most of possible scattering regimes with particular geometry of detecting system. This, for example, the OCT, we're able to imitate OCT picture. We're able to count these correlation functions or coherent properties of light and observe, the changes for different detection. We're able to imitate the reflectance spectrum for skin, for particular biological tissues, and combination of these techniques. So, and this, again, Monte Carlo of some applications available on this address, www.biophotonics.fi. And those of you who need it, so please don't hesitate to use it. It's free of charge. And also, what I should say, you can run now this Monte Carlo tool even from your mobiles. So from the you can try it even now. And that's how many people are using this our tool from worldwide, and I'm not sure, perhaps you already maybe know that. So, but it's what we worked on, and we're still working on it. So we actually we developing and will feed it with more other applications. And of course, if some of you interested to be part of this, let's say, development, so we're very welcome to collaborate, because we're now trying to do that more like international Monte Carlo platform. And we was very proud that, for example, some of our calculations was selected for the cover pages of the books by, for example, Valery Tuchin, that's his SPIE, and these pictures that was counted on, again, on our Monte Carlo technique, and now seen worldwide. So, and again, so we will continue these studies. So, and perhaps next time I will be able to give more information. Okay, what has been improved so far. So, and I'm sorry so that I have not enough time to consider maybe the particular questions. So I will be happy to discuss if you have any questions, and now ready to answer the questions if you have any. Thank you for your attention.
Thank you, Professor. Any question?
So for diagnostics, you observe an output, and supposedly you want to reconstruct what's in the air. So it's like reverse engineering, which is a highly ill-defined process. So you have to apply a lot of constraints and so on. Is this a problem, or?
Okay, so on one slide I demonstrated that this technique can be used for image reconstruction, or for inverse problem, means to understand what the optical properties of tissues are. For some reason, it's not yet available on our online tool, and the reason is very simple. So when you do this inverse problem, means when you send the light and you get output and you want to understand what optical properties of the tissues. So we able to use for that several scenarios. We can use, let's say, artificial neural network as a main tool to, to extract the information. We can use multi-regression analysis, and we can use the other smart techniques like, for example, combination of that with some Fourier transforms and some patterns and so on. Technically, it's not a problem. And we demonstrated that on some publications that we've done that. But to make it available online, we have the technical problems in terms of how to properly put it in terms of GPU. Okay, so GPU have, as I've showed, have structure of cores. And we use some GPU side for the memory when we save the trajectories of photons, and some for the counting. And as soon as for the Monte Carlo, okay, that's done. To do inverse problem, we have a choice to add another GPU, which is cost for us doubled, and it's like roughly $10,000, or to find out how it will be interact with the counting. But because it's online solution, we have no time to find the optimization of that. So we now think that it will be just additional GPU unit that will work dedicatedly for inverse problems. So it's coming, but not ready yet. Okay, but yes, it's possible.
My question is concerning the coherence of the light. So if I measure, because when I have coherent light, scattering is a little different when I don't have coherent light. Mm-hmm. So question is, if I have a volume of tissue and I use coherent and non-coherent light, mm-hmm. do I get extra information?
Yes. So if you use coherent light, so you're able to, let's say, estimate, for example, the dynamics of blood flow. Clearly, if you have incoherent light, you will be not able to do that. So you will be able to see, let's say, from our case, we use the incoherent light to observe absorption associated with changes of oxy and deoxyhemoglobin. But if we want to find out what is the actual blood flow in a particular vascular bed, so we need to use coherent light, and we use the particular laser with coherence to estimate the velocity or, let's say, some form factor of the red blood cells. So I'm actually discussed it on a previous lecture. So if you want me, I can back to some slides from there to show the difference. But coherence we think it's a powerful tool. So the problem is that it's for a number of years it was ignored because it was expensive, and now they are less expensive and it can be used more easily.
More questions? So let's thank again, Professor.